How are you doing today? We are in chapter one of water and wastewater laboratory techniques, and we're talking about analytic standards and reagents. If you're a wastewater operator, you know, uh, most likely, if you're in a small scale, you're going to do some sort of laboratory analysis, whether that be temperature, pH, DO. Maybe you're a maintenance man and you're not in the laboratory. But just having a general idea is beneficial because we have to know some laboratory when we take our water one or wastewater certification. So having an idea what happens in the laboratory, even if you don't work there on a routine basis, is important. Lab work is tedious, but it's one of the most important things we do. You know, as water and wastewater operators, we are trying to produce an effluent that is clean, or drinking water. We're trying to produce a product that is protective to the public's health. And so, lab work and being concise and having predictable and accurate numbers can really allow us to make process modifications and also provide insurance to our regulatory agency, which would be the EPA and others, that we are um, within proper standards. So, analytical standards and reagents. Chemical testing can be divided into two ways. The first type of testing measures a bulk physical property of the sample, such as volume, temperature, melting point, moisture content, or mass. These measurements are characteristically non destructive to the sample. So, if you pull a sample out of the effluent and you measure temperature, you can dump that down the drain. You really did not destroy that sample. It's still intact. Or you measure the mass of it. It's still in contact. You're not destroying. But the second type is when we add reactions or reagents. And when we do that, usually once we add a reagent, we destroy the sample. So, like your chlorine sample, um, you go out to your high service pump, pull a chlorine sample, and then you're going to put a powder packet in there, a DPD powder packet, and it's going to change that sample's color. And you're going to read that with a colorimetric instrument. Well, you've destroyed that sample. You cannot reuse that sample because we've added some sort of reagent. So that is a reagent. A standard is what we measure off of. So what we calibrate the meter to. So understanding the difference of standards and reagents, we use a lot. Most of the tests, a lot of the tests we have is a process of adding some sort of chemical or adjustment uh, chemical to that, so that we can get a analytical result. Once again, reagents allow the test to be done where analytic standards are necessary to obtain reliable results. Types of chemicals. So, the three forms of matter that are encountered in the laboratory are solid, liquid, and gases. Um, when chemicals from a commercial supplier are purchased, solids and liquids comes in gas or come in plastic or glass bottles, whereas gases typically arrived in compressed in steel cylinders. So, your liquids, maybe you get them from Blue Book or YSI or something like that. Some of your reagents that are going to come in prepackaged plastics or glassware. Your gases that you're going to use, you probably have a contract with a city, and so they bring those in uh, condensed containers to the laboratory and hopefully refill those. And so when we talk about chemicals that arrive to the plant, then we have gases, we have liquids, and we also have it as a solid matter. Many chemicals are not particularly corrosive, generating solutions at a pH of approximately 7. Some chemicals are highly acid, resulting in low pH solutions, 1 to 4. So we need to know, you know, are our chemicals acidic, or are they on the basic side, or are they on neutral? Um, when we're doing laboratory work, a lot of chemistry and a lot of what I'll call cooking is done following the SOP, but knowing what chemicals that are strongly acid or strongly base, so that we don't make a mistake in the lab is important, and also for wearing the corrective PPE. Two terms that are widely misused in chemistry are strength and concentration. So I'll highlight strength is the chemical property. It relates to the degree that the individual of molecules of the substance remain intact in a water solution or break apart into ions. A strong ion, a strong acid such as hydrochloric acid, has no intact molecules of HCI in the solution. Instead, all the molecules are ionized. Examples of strong acids. So these are ones that you could come in contact with in the lab: hydrochloric, nitric, sulfuric, and chromic acid. So, knowing the strength of your chemical, uh, if it's a strong acid, strong acids, you really need to be careful with those. Weak means the substance is largely intact as the molecules are in solution with very little ionization. Acetic acid in vinegar is a weak acid. More than 95% of the molecules are intact. Example of weak acids are your hydrofluoric, lactic acid, and absorbic acid that you would come in contact. Concentration is a physical property. It relates to how much the material is in the solution. If there's a lot of the substance in the solution, it's determined to be concentrated. If there's only a small amount uh, in the solution, it is called dilute. Strong acids are typically provided as concentrated solutions such as hydrofluoric, sulfuric, and nitric acid. A weak acetic acid provided pure 100% glacial. Although these acids are diluted before use, they are still strong acids. Chemicals found in laboratory are typically reactive, otherwise, they would be of little use. Um, so, knowing, are your chemicals active or not, reactive? Because fire is always a concern in our laboratory. Um, They can be caused by mixing oxidizers and reducers or having electrical shorts. Such chemicals as hexane, alcohol, hydrogen gas. Once a fire starts with a flammable chemical, it's very difficult and hazardous to extinguish. So, at your laboratory, you need to have a separate and safe storage for the different acids and bases that you have. Reading the SDS sheet of, can you store this with this? Keeping, in the laboratory, we have two refrigerators, one for standards, one for samples, because, we don't want cross contamination. We don't want any kind of um, uh, vaporization either. Many laboratory chemicals are toxics, and you, you should never eat in the laboratory. You should always wear gloves when dealing with chemicals, even if you do with them every day. Um, it's best to just be overly cautious when you're dealing with chemicals. We talk about acute and chronic diseases or ailments that could be caused by you working in a laboratory for several years um, with a certain chemical. So if you wear the PPE, you're going to have a better chance of extending your life. We talk about acute things, wearing respiratory or eyewear, so that you don't get a burn. Your laboratory should always have an eye wash, and it should also have fire extinguishers. And the fire extinguisher should be rated for whatever substance you're using in the laboratory um, and checked. Most pure chemicals are too concentrated for direct use as reagent. The most uh, process of dilution involves dissolving a known amount of reagent in an inert liquid called a solvent. The most common solvent in the water wastewater laboratory is the water itself. So water is used to dilute reagents. We use water to make up reagents. So in my laboratory, we make ammonia standards. We'll pipette in a 0.1 or 1 of 1,000 part ammonia standard, and then we'll add water to that, and that is the solvent that we're using, to dilute it, so that we can calibrate our meter. Water is everywhere in a lab. It's included in reagents. Some reagents have well-defined with constant amount of water in them, and these are termed hydrates. Reagents that are available as hydrates are typically available as anhydrous, meaning there is no water present. So, when we talk about water, no one do we need to dry out our reagent, or does our reagent come as a water-based product? Knowing the grade of chemicals, we need to make sure that we are um, buying a high grade reagent for our laboratory. You could go off the shelf and buy something possibly from a non-reputable manufacturer, and that's going to affect your test. That's going to affect the validity of your test. And so, knowing that there are different grades and how pure is that grade, and is that acceptable to your regulatory agency, so that you can get proper proper certificate of analysis. Each batch of manufactured reagents have a lot number and a certificate of an analysis that should be shipped with the product and are incorporated in the label of the bottle. Reliable suppliers of reagents always provide, here again, a copy of the certificate of analysis. Um, all reagents have a usable shelf life when stored under proper conditions. The shelf life may range from a week to months to years. Often, an expiration date is listed on the label. If none is listed, a year from the date of the receipt is commonly assumed. Although prepared solutions may have a much shorter shelf life, reagents should not be used past their expiration date. When we get um, uh, reagents into our laboratory, we put down the day they were received and the day they were opened. And we watch the expiration date. If it goes past the year, we pitch it, even if we have extra. So good laboratory practice is documenting all your product coming in and product going out. Using even your sample bottles, that have preservative. We put we get a new bottle, we'll put it in the back. That way, it's forcing the uh, older sample bottles up to the front, and so hopefully we were using those instead of the new sample bottle that we're getting from the contract laboratory. So just know that, everything has a shelf life, and even our reagents do also. A special group of reagents are called primary stands, are important in the laboratory. The common uh, set of characteristics are as follows. They're solid and easily purified to a reliable level. They're stable to oven dry temperatures. They have a long shelf life. They do not quickly absorb um, water on standing. Primary standards are dried in an oven at 103 to 105 before use and before use to remove any absorbed water. So, like for us, when we do BOD for our GGA, we have powder. And so on a Wednesday, I will put that powder in the oven at 103, and that just makes sure that we remove any kind of moisture that may have collected, in the bottle. And so that'll dry. So that when I'm measuring out that powder, obviously if that powder had any kind of moisture in it, it's going to affect the total weight of that. And so, we want to make sure that when we're weighing out those granular reagents, that we're weighing them at the same consistency of, um, of water moisture intake. As mentioned in previous sections, chemical reagents can be classified as acids, bases, oxidizers, reducers, flammable solvents, gas cylinders, and miscellaneous. Reagents should always be segregated according to class and stored in separate areas. So on the bottom of page 10, you see an acid storage container, nice metal one. Um, it says some reagents and standards must be stored at a lower than room temperature. You can have an explosion proof and chemically resistant refrigerators should be used. Knowing how you're supposed to, or can you store those in 70-degree weather, or is there special, should your reagents be stored at a cooler temperature? When it's shipped, receiving it from the manufacturer, was it at temperature when you shipped it? All these things go into the verification of accuracy for reagents. Water is most commonly found in laboratory. Uh, when we talk about water laboratory, we're not talking about the tap. We're talking about highly purified water. Water that has went through a deionized unit. Um, Deionized cartridges are filled with either aonic specific or kaonic specific exchange resins. Um, and we want that water to be as pure as possible. If you've seen in your like my dishwasher, when it gets out there, there's that residue of hardness that is on that glassware. And so your glassware should be pure of any kind of, mineral content or anything else that could cause some sort of detrimental reaction to whatever standard that you have in there. Um, so it's important that we have pure laboratory water. We also want to have water that is free from bacteria. So when we do like a 5-day BOD test, we'll fill the blanks up with laboratory pure water. We'll measure the water at a with a DO probe, making sure. Let's say it's 8.63. Well, when we read that out in 5 days, we want that water to read 8.63. If it reads 8.21, well, we know that there was bacteria in the water. So, you know, that's why our laboratory water usually will run it through a reverse osmosis, possibly through a deionized system. And then also, I prefer running it through a UV light just to make sure that, our water is, our laboratory water is free from bacteria, because bacteria over time, when we add that with our reagents in any test that we use, can obviously cause um, a discrepancy in our results. Well, that is it for chapter one. I appreciate it. Thank you.